These are the notes for Honors Geometry 9.6, which is called Apply Properties of Chords. So we've learned what a chord is back from Unit 9 at the beginning, where a chord was just a segment where 2 points are on the circle and they're connected. So any 2 points on the circle, as long as they connect only on the circle and not like to the center only, they have to physically be 2 points on the actual circle. Now sometimes they'll pass through the center and that would be like a diameter, but specifically today we're going to just look at chords that are not always diameters, or like there's a bunch of theorems that we're about to cover today that will apply different things that happen when you have chords in circles. Okay, so there are 4 theorems that we're about to see. Let's first figure out what they all say, and then we'll be applying each one. And so when you see a question, our first question will say, well, okay, which theorem are we trying to apply, and then how do we actually answer it? So the first one says, in the same circle or incongruent circle. So although the diagram shows just one circle here, it can be possible to have this same scenario with 2 circles that are just congruent to each other. Remember, congruent circles need to have the same radius. So in this same circle, it says 2 minor arcs are congruent if and only if their corresponding chords are congruent. So this is showing us that arc AB, so this is talking about this arc right here, and it's saying if that arc is congruent to this one, CD, then that the chords AB and CD would be congruent as well. So that this would be chord. Remember when we write this about chord, it's a segment symbol on top here. So then we'd have AB is congruent to CD, like this. And that's all we have just for, it works both ways. So because this says if and only if, you can technically say that if you know the chords are congruent, then their arcs will be congruent. Or if you know the arcs are congruent, then you can say that the chords would be as well. So you just have to see which arc is being created. What does the arc that's being created from the chord? Make sure you're looking at specifically what arc it is. It helps to outline it like I just did here, or use a highlighter if you'd like to do that instead. Both things are pretty helpful for that. Okay, so let's try a few. The next one, same idea. The next one says if one chord is a perpendicular bisector of another chord. So you're going to still have 2 chords in this diagram. In a circle, we have 2 chords where it's saying that one is a perpendicular bisector. Make sure you're looking at both words there. We've seen these words before, but perpendicular means you'll see the right angle drawn in, that the 2 lines are perpendicular, and bisector means it's like the midpoint is happening right there too, because the segment is bisected. And so when that happens, it's saying here that the first chord has to be a diameter. So this is an if-then statement, and this is what that theorem is saying. So in this diagram here, because segment TR is the one that's a perpendicular bisector, notice that it's being bisected, it's got the right angle, that means that QS would be the diameter of the circle, because it's saying here if segment QS is a perpendicular bisector of TR, because QS is the one that's doing the bisecting. It's cutting TR into 2 equal halves, or 2 congruent halves, and then also creating a right angle there. So when that happens, then it is a diameter. So that helps sometimes to know if something is a diameter, because notice from the first picture, we don't know if any of these are diameters. But this one here, even though the center is not labeled, we now know that QS is a diameter because it meets this criteria. So as long as you're looking for both perpendicular and bisector, not just one of them, it has to have both in order for this to be a diameter. Okay, 10.5 says, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So this is similar to the last one. It's almost like, think of it the other way around. So it's saying here that now you know that EG is a diameter. So segment EG in this diagram, it is a diameter. Notice it also labels the center there for you, because this time that would be like what you know for sure to start with. You would also know that segment EG is perpendicular to FD. So we'll draw that little perpendicular symbol. If you know both things are true, now you can go on to say that the segment HF this part right here, is congruent to segment HD. So it's kind of the converse of theorem 10.4, you could say, but it is it's not just going straight to the perpendicular bisector. It is saying here that these two things have to be true, and then this is telling us that it's bisected. It's also going on to say here that the arc FG, this arc right here, is congruent to arc DG, because same kind of thing as what happens on the first theorem, the arcs and the chord that corresponds to it, those are congruent. So it's kind of that idea, it's kind of combining almost 10.3 and 10.4. Okay, and then 10.6 says, in the same circle or in congruent circles, again, this diagram only shows one circle, but it can be the case if you have two circles that are congruent to one another. Remember, the radius would have to be the same. The two chords are congruent if and only if they are equidistant from the center. So if you see that segment, in this case, segment AB is the chord, and CD is another chord. So they're saying if we have two chords that are congruent, so let's say specifically we're talking about segment AB is congruent to segment CD, then you can go both ways here. You could say then we know that EF, so this distance here and this distance here, we'll put the little tick marks if that helps to see, that those would be congruent anytime you know that you have these chords. But it's also going to work the other way around, where EF and EG will be equal to each other. If that's the case, then you also know that the chords are congruent. Okay, now, and then once you know the chords are congruent, that goes right back to theorem 10.3 again with the arcs being congruent. So there's lots of overlap with some of these theorems, but we're going to kind of take one at a time to make sure we really understand what each one says and then how to apply it. Okay, so that's a little bit about each of those theorems. On this diagram, you are going to notice the right angles here, and that has to do with when you draw the segment here, the segment for EG and EF, it will be perpendicular to both of those chords, similar to like what a perpendicular bisector would be like, but it's not a perpendicular bisector because the perpendicular is happening at this point with the chord, and these are being bisected separately. So it doesn't say that the chords themselves are being bisected. We only know about the segment that connects, or like the distance to the center. That's the main idea here. All right, so let's move on to how to like apply these. And so I'll do the first two with you guys, like down here. Then I'm going to have the sub pause the video so that you can try out some of the ones on the next page, and I will have the sub replay the video so that you can see the answers for the rest of them as well. And Canvas will have both this video and an answer key. The answer key is posted already on Canvas for this. Okay, so what theorem allows you to answer the question? That's what you're going to ask yourself first. Like, is it theorem 10.3, 10.4, 10.5, or 6? You don't technically have to memorize the numbers of the theorems. Like, you don't have to say this is theorem 10.5. But for the sake of practicing these, I'm going to reference the numbers. But when it comes down to actually knowing, what to do in a problem, when you see a diagram, you just have to, remember what was one of those theorems, what did it say? But if it helps you to remember the numbers, go for it. Alright, so we're going to figure out which theorem we're applying. Then it says, how do you know you can use that theorem? And now go ahead and answer it. So looking at the diagram, it looks like I have two chords here, but they're not congruent to each other. But in two circles, notice that the radius of each circle, they're congruent, right? This is showing me that this is the radius from the center to this point. It's saying it's the same thing as the center to this point. So already we're finding out that the circles are congruent to one another. And then I see an arc measure here of 125 degrees, and I have a chord that kind of corresponds to that 125 degrees. And I have in the other diagram, again, this is they're congruent circles. I'll first kind of mention that because the radius are congruent. And so this chord BC is saying that it's the same as chord EF, since those are congruent. That means that their arcs are going to be congruent, or that their arc measures are equal, therefore they're congruent. So to answer these questions, the first question says which theorem? This is the first theorem, 10.3, or theorem 10.3, if you want to change around the order. how do we say that, just to match it to the top. So just to move this up for a second to show you again, Theorem 10.3 says it can both directions. It could be, it could be in the same circle or congruent circles. So although this diagram only shows one circle, the one we just looked at had two circles that are congruent, and that their minor arcs will be congruent if and only if the corresponding chords are congruent. So that's what we're seeing here, that the chords EF and BC are congruent to one another, so that's why we know that their arcs will be congruent. So to kind of give a little bit of an explanation, not a whole lot, but just I'll write down that the circles are congruent first of all, and the chords are congruent. You could say which chord specifically. You could say BC is congruent to EF if you wanted to mention that, but really we just have to answer the question, which is, in this case, if the measure of arc EF is 125, then the measure of arc BC is also 125 degrees. So this is really the answer. You don't, like on a quiz or a test, you're not going to have to do all this explanations, like which theorem is it, how do you know? Most likely it'll just be like a picture, and it'll say, what is the measure of arc BC, and you would just say, okay, it's 125. So although this seems pretty simple, the hardest part of this is because there's 4 theorems to keep track of, and there's more later on, not for some time now, but we are going to add more theorems later on. For this first quiz that's going to come up next week, though, these 4, you want to make sure you know them well and not confuse them kind of for each other. Okay, so let's try the next one. Same kind of steps that we're going to follow. We're going to first figure out which theorem does this look like, and it's honestly very similar to one of the pictures already from above. So if you look at the different options, it looks a lot like this picture, right, where the diameter, it's showing us we have a diameter because of the center, and it has a right angle because it's perpendicular, and now we have to know what that means. What is it that Theorem 10.5 tells us? So in circle E, it tells us that's the center because then segment AC is the diameter. So this is Theorem 10.5. We're applying this theorem. And then for my reason, you don't have to, again, write very much, but we'll say that AC is a diameter. And we know that, again, because it's circle E, or the center is E. And once I know that it's a diameter, and we have to say what the two segments are that are perpendicular. So AC is perpendicular to BD. Segment AC is perpendicular to BD. That's how you know that Theorem 10.5 tells us then that the length of BD is going to be, remember it's a perpendicular, it's a bisector. It's like bisecting it so these two are the same. So BF has to also be 6 then, so that BD would be 12. So the final answer is BD equals 12 because it has to be 6 and 6. All they gave us was this little 6 here, but that was enough to be able to find BF, which is also 6. Now the arc measures were not mentioned, but if I also knew anything about arc BC or arc CD, I could then know that the other one would be the same as well. Okay, so this is where you can pause the sub can pause the video, and then you guys can try out the next page of this. Is all lots more practice. All of this says practice, and again doing the same thing. Look at the diagram, try to figure out which theorem to use. How do you know that that's the theorem you want to use, and then try to answer it. That's how it is for number 1. And then number 2, just using the diagram, and specifically this is a lot of algebra. You could skip over some of that algebra for part C, but I will still go over it in the video if you're interested, or you could choose to just not watch all of it at that point. But that would be for number 2. And then finally, number 3 on the next page has another diagram, and then again you're finding some of the missing pieces for those. So, and then 4 is more open-ended. There's lots of different answers that you could have, so I won't necessarily go through it in too much detail. But go ahead and try some of this out, or you can move on to the homework first if you'd like to, but I'll have the sub play the rest of the video and